Okay, so today the topic of discussion is the design of T and L beams in Flexure, and we people already have a insight about this topic. We already discussed it in the class, but let me again go through very briefly through the introduction of T beams and L beams. So the topics of this would be introduction to T and L beams, the ACI code provisions for T and L beams, design cases, design of rectangular T beams, design of full T beam, and references. The objectives are that at the end of this lecture, students will be able to differentiate between T beam and L beam and its difference with the rectangular beam, explain mechanics of rectangular T beam and true T beam, and design of T beam for Flexure. Now, introduction to T and L beam. As you already know that the T or L beam gets its name when the slab and beam produce the cross sections having the typical T and L shapes in a monolithic reinforced concrete construction. So you can see the encircled portion in the figure. This is a beam and this is a slab. So it is making configuration of T. Okay. So if you can see that this beam and it has only a slab at its one side, so it's inverted L. So these beams they got the name with their configuration, the geometric configuration. That's why they are called T beams and L beams. Casting of reinforced concrete floors, roofs, the forms are built, formwork is built for beam sides, the underside of slabs, and the entire concrete is mostly pure poured advance from the bottom of the deepest beam to the top of the slab. Okay, so first the reinforcement has been fixed, and then the concreting has been done at the same time, so that the concrete of beam and column is poured simultaneously, and this is called monolithic construction. And this is the basis for the reinforced concrete structures, and we make sure that the concreting of the slab and beam is done simultaneously at the same time for a better performance and bonding of the concrete, and also because to avoid the construction joint within the element or member. Okay. Now, this is a simple behavior. You can see that two span beam resting on columns or walls, whatever it is. Let's assume these are the walls, and these are the roller or hinge supports. Okay, so there will be zero bending moment at the supports. There will be maximum positive bending moment at the center, maximum negative moment at the interior face of the support, and then maximum positive bending moment. So what is happening here that at this point, at section AA in both of the beams, the compression will be at the top, and since we have discussed that the slab will be acting as a part of the beam, so the slab will be acting as a part of the beam, and the compression will be in the slab and or in some part of the beam web. Okay. However, at section BB, where there is a negative bending moment, so there will be tension at the top portion of the beam, including the slab, and there will be compression at the bottom of the beam. Okay, so we understand that in case of negative bending moment, there is no problem, no issues regarding the behavior, whether it will be a T beam or rectangular beam, because the bottom of the beam, which is completely webbed, it is in the tension, and it is in compression, and you have designed it for the as a single reinforced beam. But in the positive bending moment, the top of the beam is in compression, and the top includes the part of the slab. So in that case, you have to be careful. In the analysis and design of floor and roof systems, it is common practice to assume that the monolithically placed slab, see, as I explained previously, that monolithically placed slab with beams and supporting beam interact as a unit. Okay, so if it is monolithically placed, then they will act as a unit resisting the positive bending moment. Okay, as shown here, the slab becomes the compression flange. See, in the previous lectures, especially in the design of singly reinforced beam, we have seen in history that the top of the beam is in compression and the bottom is in tension. However, in this case, the slab is acting as a part of the beam, so the part of the slab or the completely slab, full flange slab will be in compression. Okay, while the supporting beam becomes the web or stem. So there are two different parts of the beam now. One is this flange part, which is actually slab, but acting as a part of the beam, and the other is this web. Okay, so the thickness of the web or the width of the web is different than that of width of the flange. Similarly, the flange height or the flange depth is different than the depth of the beam. Okay, so you have to be careful in these terminologies. As I mentioned on previous slide, that negative bending moment will not be a problem. In case of negative bending moment, the slab at the top of the stem will be in tension. See, the slab is in tension. Also, this part of the beam is in tension, while the bottom of the stem, this web, this is in compression. This usually occurs at interior support of continuous beam, as we have seen previously. So for T and L beams supporting monolithic or composite slabs, the effective flange width BF. Now we will be using this terminology throughout BF. Okay, shall include the beam web width BW plus an effective overhanging flange width in accordance with ACI 31819 table 6321. Okay, so ACI says that okay, if you are taking the part of slab, the part of slab that is acting as beam. So, how much will be the width of that effective slab width? So, ACI has given some values in table 6.3.2.1 for T beams and for L beams. Okay, so this BF, which is effective flange width, will include the BW, which is width of the web. Or previously we were just taking it as a B. Okay, if you remember, point X is right into B or A into B. So the difference between the BF of T beam and the L beam will be that in L beam the BF will be BW plus this flange width on one side. However, it will be on both sides of the beam web. Okay, so this is we called as web, and this we called as flange. The height of slab in this case will be called as height of flange. Okay, and width of flange BF and HF. So you should be careful in with these terminologies. The difference, sorry, not difference, the distance between the webs or the stems is termed as SW. Okay, it is a clear distance and not center to center distance. Okay, so please keep in mind that this is basically slab, right? And we are taking a part of slab as a beam, and we are calling it as a flange. Okay, you should keep in mind. Calculation of effective flange width, as I referred you to SI table 6321 on previous slide. So it says that for T beams, number one, the effective flange width BF is equal to BW plus 16 into HF. Now you know the HF is the height of the flange or the slab depth. Number two, BW plus SW. You know SW, it is a clear distance between webs of the beams. Okay, and third one is BW plus Ln divided by 4. You know BW, okay? This is the web width or width of the beam, actual beam. Ln, what is Ln? So it says that Ln is the clear length of the beam. SW is the distance between adjacent beams, okay? So if there are two parallel beams, so the distance between, the clear distance between both of them is SW. However, Ln is the length of this beam. So least of the above values is selected as BF. For example, it gives you 100, the second one gives you 96, and the third one gives you 84. So 84 will be your value of BF, okay? And you took it as a use in the calculations. So note in ACI 31819, H is used for slab thickness, while in ACI 31819, 6321 H is used as slab thickness. However, 9311 this lecture for differentiation between beam depth and slab thickness. HF will be used to denote slab thickness. Okay, so we are using HF instead of H. Similarly, for L beams, there are three equations, and the least of these values will be used as a VF for L beams. Now, coming to the design cases, in designing a T-beam for positive bending moment, there exists two conditions. Number one, the depth of the compression block may be less than or equal to the slab depth, that is flange thickness. Okay, this is good. I am telling you here that if you got this, then you will be happy. The depth of compression block is less than the height of the flange or depth of the slab. See, so in this case, this portion of the slab that has been highlighted is in compression, and the rest of the slab and this portion of the beam, you have not to worry about that. Okay. In such a condition, the T beam is designed as rectangular beam. So forget everything and design your beam as a rectangular beam, just like you have designed in your previous lectures. For positive bending moment with the width of compression block equal to BF. The only change in this case will be that instead of B, you are using now BF, and you know how to calculate BF. You know the formulas for T beam, you know the formulas for L beam. And as I explained earlier, that T and L are just their geometric representation. Okay, the not T beam design. T beam design is different. Okay, so in this case, if your A, the depth of compression block is less than HF, for example, your HF is 6 inches, okay, and from calculation you are getting your A as 5 inches, so 5 is less than or equal to 6, good, so design it as a rectangular beam and you're good. However, the second case will be a bit difficult, okay. This is your case number 2, where the compression block cover the flange and extend into the web. For example, HF was 6 inches, okay, and your A is now 8 inches. In previous case, the 8 was 5 inches, which was less than HF. In this case, let's suppose A is 8 inches, which is greater than HF. Now your beam will be designed as a true T beam, because now this complete portion of the slab is in compression as well as this part of the beam is in compression. See, this is A and A is greater than HF and A is extending to the web portion. So now there are some difficulties. This is not very difficult, but there are some difficulties as compared to case 1. Okay. So this is a true T-beam. However, the previous one was a T-beam just by its geometry and not by its design or mechanics. Okay. So now we will go deep into design of true T-beam. Okay, so now starting with the case 1, when A is less than or equal to HF, as I gave you example that HF is, let's suppose, 6 inches and your A after calculation is 5 inches. So this is a simple case. This is your A, this is your BF, this is your HF. Your neutral axis has been calculated. The depth of the beam is D, the width of the beam is BW, and the area of steel is AF. Okay, we are good with the terminologies. So starting with the flexural capacity of rectangular beam, okay, keep in mind that if A is less than HF, then this is rectangular beam. Why rectangular beam? Because only this rectangular portion is in compression, just like previous cases, okay. So taking the equilibrium equation, summation of f of x is equal to 0. Now consider this stress diagram. This is your strain diagram and this is your stress diagram, and from this you are making these forces, calculating these forces, the tension force and compression force. You know the area of these compression block, right? What is the area of compression block? This 0.85 FC prime, this A and this B, and previously it was only B, this case it is BF. So there is no change except BF. So 0.85 FC prime A into BF. This is your area of compression block and this is your compressive force. And tensile force is simple ASFY. So you can get the value of A from this equation, which is equal to ASFY divided by 0.85 prime BF. Okay, this is your first equilibrium equation. You can get second equilibrium, summation of moment is equal to 0. So Mn is equal to this tension force multiplied by this moment arm or lever arm, okay, which is equal to d minus a by 2, which is very simple. So ASFy into d minus a by 2, and you can solve it for AS, and you can get it as mu divided by mu, or you can get it as phi mn divided by fy, phi fy into d minus a by 2. Okay, the other checks remain same as that of rectangular beam design. So note that in calculating as maximum and as minimum, use bw not bf. Okay, so while you are calculating as maximum and as minimum, you have to use bw. Why you are using bf here, and why you are not using BF here? The answer is very simple, because here you are calculating this area, right? This is the compression block. However, when you are talking about As maximum and As minimum, so As maximum and As minimum, you are using this area, because see, you are designing this portion, the tension part, you are designing steel for this tension part, and for the tension part, the tensile steel is in the web, not in the flange. Okay, so if you are designing for the web, you have to use the values of BW and not BF. So please keep in mind this simple concept, okay? And this is our example one on the rectangular T-beam, not a true T-beam, okay? The roof of a hall has a 5-inch thick slab with beams having 30 feet center to center and 28.5 feet clear length. So you got the length of the beams, you got the thickness of the slab, which is HF. The beams are having 9 feet clear spanning, so you are getting SW, okay, and have been cast monolithically with the slab. So it fulfills our condition. Overall depth of beam, including slab thickness, being 24 inch and width of beam web being 14 inches. Okay, so you are getting the depth of the beam as 24 inches and width of the beam as 14 inches. Now what it asks is calculate the steel reinforcement area for the simply supported beam against a total factored load. You have to include the self weight of beam and of 3 kg per foot. Okay, so it includes the self weight of the beam. You don't have to include the self weight of the beam. Use fc prime is equal to 3 ksi and fy is equal to 60 ksi. So you have to design your beam for these conditions. Starting with the solution, span length is 30 feet, clear length is 28.5 feet, WU is given 3 kip per feet, D of the beam is 24, so minus 2.5 is 21.5 inches, BW is 14 inches, HF, which is slab thickness, is equal to 5 inches. Effective flange width can be calculated with the data given to us. You have to plot this data in the figure for better understanding. Okay, so you had 24 inches of total depth and 5 inches of slab, so this 24 inches of complete depth minus 5 inches, so you are left with the 19 inches. Okay, and this is the depth of the steel, effective depth of steel, tension steel. So these are the three equations from ACI 6.3.2.1. You are putting the values and getting the answers. 94 inches, 122 inches and 99.5 inches. So least of them is 94 inches. Therefore, your effective flange width is 94 inches. Okay, you got this data. Now, the most important check in the T-beam is check if the beam is behaving like a T or a rectangular. And you can check it by comparing your small a with the HF. Okay, so mu you are given with the WU, so you are calculating mu, which is equal to WU L squared divided by 8. You are using L center to center. Okay, so in this case, your MU is 40-50 inch kips. File number one, let A is equal to HF. You are directly taking A equals to height of flange. Okay, so let's take A is equal to HF and put it in the equation of AS. You calculate AS and put it in the value of small a. You are calculating small a, which is 0.98 inches, as it is much lesser than HF. So your beam is acting as a rectangular beam. It is not a true T beam. Okay, so therefore design as a rectangular beam. And calculate AS on the basis of this small a. So your AS is equal to 3.56 square inches. Got it? So going to a third trial, recalculate small a, which is equal to 0.89 inches, and put again this value in the AS equation, and you will get 3.56 square inches. Therefore, your area of steel is equal to 3.56 square inches. Using number 8 bar, number of bars will be equal to steel area divided by bar area. So you are getting 4.45. It means you are using 5 number 8 bars. Now you're done with the design. Just check the maximum and minimum reinforcement ratios of ACI. So as I mentioned earlier, that you will be careful. You have to be careful that you are using BW, okay, in these equations. So putting the values in this AS minimum equation, and you are getting the value of 0.82 square inches and 1 square inches. Therefore, greater of them is 1. So take AS minimum as 1. So you are good. Now check the AS maximum. This is the AS maximum equation, and keep in mind that you are using BW and not BF here. Okay. So your AS maximum is equal to 4.06 square inches, right? So AS minimum is 1, AS maximum is 4.06, and AF is 4. How it is 4? Because you are using 5 number 8 bars. So 5 number 8 bars give you 0.8 into 5 is 4 square inches. Okay, so you are slightly okay. It would be better if you use different bar number, so that, for example, if you are using number 6 bar and the area of steel is coming 3.8, so it will be much better to keep a bit away from AS maximum. But this design is also okay. And this is your final drafting. See, nothing special was in the design of this beam. It was very simple because you already know this. You have already done this many times. I have given you a lot of assignments and examples we have solved in class. So you people should know how to design this. The BF is 94 inches, BW is 14 inches, total height of beam is 24 inches, height of slab is 5 inches, and this is your design. You are using 5 number 8 bars, okay, in 2 rows. You have used 3 bars in the bottom row, 3 plus 2 in the top row, okay. So this is your what you are calling design of rectangular T-beam, and the next will be design of a true T-beam, okay. It was designed as a class activity, but since there are no classes and the thing is online, so go through it, design the beam B1, which is B1. You can clearly see this is B1. For the following movements, material properties are given, beam dimensions are given, slab thickness is given, overall beam depth is given, and the moments are provided. Okay, so just design for these movements. This is your homework. You have to do this. And now the special case, a true T beam, design of true T beam, where A is greater than HF. When A is greater than HF, see this case. So your A is greater than HF because your complete slab is in compression, plus this part of web is in compression. Okay. So you have to do, what you have to do is you have to split it. Why? Because width of the web is different and width of the flanges are different. Similarly, the depth. The most important thing is depth of the flanges is different. For example, this portion is acting differently than this portion. Okay. So what we do is we take these flanges, we took their effect differently, and we use this web and we take its effect differently. So for web portion, we use the depth A with the width PW, and for the flanges portion, we took the depth HF and the width of BF minus this BW, because we are excluding this portion. Okay, so there will be two moments. If you remember the design of doubly reinforced beam, so it is more or less like that. In doubly reinforced beam, we were taking two moments. One was due to compression steel, and other was due to compression in concrete, and both of them were making moment along with the tension steel. Okay, so similarly in this case, there will be two reinforcements. One will be making movement with the compression in flange, and other will be making movement with the compression in the web. So phi mn1 plus phi mn2. Okay. So keep in mind that this design is more or less is like doubly reinforced beam. If you remember, so coming to the mechanics and using the same thing, calculating the phi mn1, and phi mn1 is about the flanges. You know the depth of flanges HF, and you know the width, which will be equal to this BF minus BW divided by divided by 2 is this, and divided by 2 is this. So completely it's BF minus BW. So using equilibrium equation, T1 is equal to C1. It means that C1 is compression of flanges and C2 will be compression of web. So C1 and the portion of tension reinforcement that is balancing this C1 is T1. Okay. So C1 is equal to 0.85 Fc prime, and as I told you that width will be Bf minus Bw and depth will be Hf, and in the second case it will be Bw into A, okay, small a. Similarly, T1 will be equal to ASF Fy. What is ASF? F means flange. So that part of reinforcement that is making movement with the uh, compression in flanges. Okay, so there will be two steels, ASF and maybe ASW or AS. So ASF Fy, which is tension, is equal to compression 0.85 Fc prime Bf minus Bw into Hf. Everything in this equation is known except one thing, and that is ASF. Therefore ASF can be easily found. Once you have found ASF, you can find phi mn1, which is equal to T1 into this L1, and L1 is equal to D minus not small a by 2. Okay, you are using flange, so D minus HF by 2. You know that the height of the flange is HF and its centroid will be at the center. So this is very simple equation, phi ASF Fy into D minus HF divided by 2. So this portion was much easier, right? Now coming to the second portion where we are using the compression in the web. So in this case, the depth of the block is small a and width is BW. So see, as I mentioned you on previous slide that we will be using T1 and T2. Okay, so T2 is equal to C2. C2 is equal to 0.85 Fc prime a small a into BW, and T2 is equal to, we have just used ASFY. Previously it was ASF. So ASFY. Now ASFY is equal to, which is tension, and C2 is equal to 0.85 Fc prime small a into BW. We can find small a from this equation, and similarly we can find AS from this equation. Okay. So AS calculation, we know that phi mn is equal to mu. Now mu is equal to phi mn1 plus phi mn2, as there are two moment capacities. We already know phi mn1 because we know HF and we know ASF. Okay. Therefore, phi mn2 is equal to this demand minus this one. So we will get phi mn2. Okay. Now this phi mn2 is equal to phi ASFY a to d minus a by 2. You simply find out AS and small a and calculate area of steel by trial and success method. Okay. So we will solve an example and it will give you a much clear idea about design of a true TP. So once you get the values of area of steel, then you have to check the ductility requirements, and you have to check that T is equal to tension is equal to compression in flange plus compression in web. Okay, so AS total, AST means AS total area of steel into Fy is equal to C1 is 0.85 Fc prime Bf minus Bw into HF, and C2 is 0.85 FC prime A into BW. Now you know this thing that phi mn1 is equal to ASF into Fy, and you know this thing 0.85 FC prime A into BW. So for ductility, epsilon S steel strain is equal to tensile strain, which is equal to epsilon Ty, this one, uh, and uh, this concrete should reach its ultimate strain, which is equal to 0.003, and this is the requirement of SCI table 21.2.2. So for A is equal to beta 1 into C, AST, this total area of steel will become AST maximum. Okay, therefore AST maximum into Fy is equal to 0.85 Fc prime beta 1 C into BW plus this term ASF into Fy. For Fc prime less than or equal to 4000 psi, you know that beta 1 is equal to 0.85. If you are using higher grade concretes, so it will reduce 0.05 for each 1000. Okay, so now AST maximum is coming from this equation, and it is this value. Alternatively, AST maximum for true T beam can also be calculated from AS maximum of CPD plus ASF. So for T beam to behave in a ductile manner, AST total area of steel provided should be less than or equal to AS total maximum for a true T beam, which is from this equation or from this equation. Okay. By the way, we already discussed these things, that how you can calculate this C is equal to 0.375 into D, okay, in the previous lectures. This is our design example 2 and design of our true T-beam. It says that design a simply supported T-beam to resist a factored positive moment equal to 6700 inch kip. The beam is 12 inch wide and is having 24 inch total depth, including a slab thickness of 3 inches. The center to center and clear lengths of the beam are 25.5 feet and 24 feet respectively. The clear spacing between the adjacent beams is 3 feet. Take these material properties. So this is the given data: span length of beam and clear length, the effective depth, width of the web, height of the flange or the slab. So we can calculate effective flange width is minimum of these, and we can get this 48 inches as the BF effective flange width. Now it says that check if the beam behavior is T or rectangular, and let A is equal to HF, just like we did in the previous example. So A is 3 inches, put it in the equation of AS. So you are using 3 inches and it turns out to be 6.2. Wow. And you are using this 6.2 in the equation of small a, and it's 3.041 inches. Oh, slightly greater than this 3 inches. Okay. Therefore, design as true T beam. Got it? Now, coming to the design, calculate ASF as is the easy part. So we remember the equation of ASF is equal to 0.85 Fc prime Bf minus Bw into Hf divided by Fy. Now we know each and everything in this equation. Just put the values and get ASF is equal to 4.59 square inches, right? So we got ASF, put it in the equation of phi mn1, and you get the value of phi mn1 equals to 4957.2 inch kip. Now you got phi mn1, you know mu, then you can get phi mn2, and from there you can just simply get AS and small a. So the nominal moment resistance phi mn2 provided by remaining steel AS is, as I told you, that phi mn2 is equal to mu minus phi mn1. So the remaining is 1742.8 inch kip. Now let A is equal to 0.2D. Find AS, which is 1.667. Use it in the equation of small a, which is 3.27. Values are different, so use another trial, so by trial and success method, final AS comes out to be 1.62 square inches. Now, the total area of steel is equal to ASF plus AS, which is equal to 6.21 square inches. So use 9 number 8 powers. So total provided area will be equal to 7.2 square inches. This is the actual area of steel that you are providing. Now for ductility checks, this should be less than or equal to ASP maximum for the T-beams. Okay. So ductility requirements AS minimum should be less than or equal to AST, and this AST should be less than or equal to AST maximum for true TB. So these are the values or equation of AS minimum. Just put the values uh, and it's for less than grid steel. Okay. So putting the values gives us a value of 0.86 square inches. Okay, we are good. Now, uh, as we have seen in the while discussing the mechanics, that AS total, this value AS total maximum is equal to AS maximum plus this ASF. So AS maximum simply is, we know this equation, 0.27 FC prime divided by F point two BD, and we also know how this 0.27 comes from, where it comes from. So no need to confuse. So 3.48 square inches is your AS maximum singly, and you know the value of ASF, so just add them together, it comes out to be 8.07 square inches. So your provided area of steel is 7.2, which is less than AST maximum for true T-beam and greater than AS minimum. Okay, your design is okay and you are good to go. And coming to the important part, the drafting. So this is BW 12 inches, this is BF 48 inches, HF 3 inches, effective depth recalculated based on 3 layer of reinforcement provided, 3 plus 3 plus 3, number 8 bars, 9 number 8 bars have been provided. Okay. And one important thing is left, which is an activity you have to perform at home. And what is that? This is the activity that you have to perform at home. Basically, it was designed as class activity, but now you have to do it at home. The area of steel that you have obtained, the 9 number 8 bars. So check design capacity yourself. Okay, that what is the final design capacity and whether it is greater than the MU or not. So you have to perform it at home. And finally, these are the references. The design of concrete structures for 14th edition book and building code requirements for structural concrete ACF 318 2019. So thank you very much. This was all about the design of D-beam. And if you are asking about L-beam, so there is nothing to worry about L-beam. It is similar to T-beam, just you have to consider the one side of slab, and the equations that I already provided you on the slide you have to be used for the calculation of the BF, and on the basis of that the rest is similar to the T-beam. Okay, so no worry about the difference. There is no difference between the T-beam and L-beam. The only difference is that T-beam is on both the sides and L-beam is on one side. Thank you very much.